talk loud. I'm Dr. Steve Duranso. I'm one of the faculty here at University of Central Florida. So welcome to our campus. Hopefully the instructions and directions were good. So the bus made it from Miami, so that's always a good sign, right? I think we're missing one group that's on the road from Tampa, so hopefully they'll make it here at least in time for lunch. So here's our program. Is we have our posters and the ones that are there, and we will go through the lecture, and then after we're done in questions and answers and that, we have boxed lunches ready for you. There's vegetarian, for those of you that requested vegetarian, so we have several of those. We have several varieties of other ones. It's the same cookie for every single one, so there's no cookie transfer or negotiating involved in that, okay? So we're fortunate here to have this, obviously our guest speaker today. As far as their presentations are concerned, the copies are available to anyone, both lectures, if you want them. I'll be the one that if you want to contact me to get a hold of them, we'll make sure that you get them, we'll get them to you. Those of you that know how to get a hold of me, my information is on the packet that was sent out with the program packet for this announcement for this lecture. Dr. Tchobanoglous is, as you know, very well known in the industry. Probably most of you all know of his work. He's done, obviously, wastewater projects. He was the first to do aquatic plant work, demonstrating the use of aquatic plants in wastewater treatment technologies. Up to that point, if you really understand what was going on in the industry, that nobody had done that. And so that was significant. He's done UV, and he's done coagulation and sedimentation. So pretty much anything environmental engineering related, he's probably touched upon, consulted upon, or advocated or counseled on. I would not want to be on the other side of the witness table on his depositions, that's for sure. So we're very fortunate to have him. He obviously is a professor emeritus at UC, University of California, Davis. And Davis, for those of you who don't know, is north. It's near Sacramento, so it's in Northern California, so don't confuse him being from Southern California, because that's not a good thing to do with Northern Californians. We do a lot of work, my group, we do a lot of work in Alameda County, which is in Silicon Valley, and they remind us all the time they're Northern Californians, not Southern Californians, so it's a big deal, just a hint there. And so we had two different talks. The way that Kappe works is that you get to pick and choose two talks. So unanimously, the universities that were involved requested to have him talk on the reuse issue. And so it's an entertaining lecture, and we have lots of time, and it's all yours.
Thank you. It's great to be here, and I want to thank you for the invitation. And what I'd like to do today is share some thoughts with you on direct potable reuse, and I call it the path forward. That's not a good sign. Well, here's the overview of the presentation. How long was the bus ride? 3 hours? Pretty close. So what I'd like to do is kind of give you an overview of direct and indirect potable reuse, and then really sort of focus on the technology, because if we're going to do effective potable reuse, we're going to have to reinvent wastewater treatment. And it's a marvelous opportunity for you folks, because you're going to be the folks that are going to, in fact, reinvent it. And we'll talk about how it ought to be reinvented. Now, I'm only going to ask one favor. On the overview, on the next slide, I'm going to ask you all to read it with me. I know. But just do me the favor. Wastewater
is a renewable recovery source of potable water, energy, and nutrients.
And that's kind of the thrust of the presentation. I'll keep coming back to that theme as we go through. But it's really important to think about that. In the 20th century, wastewater was a waste. In the 21st century, we cannot think of it that way. It is a resource, and it is recoverable, and it is renewable. You know, the types of reuse, and I'm not going to linger on this, but there are a variety out there. Obviously, agriculture worldwide has been, and I've highlighted some of the problems that we have, and I'm not going to go through those, but we have agricultural, landscape, industrial, and then we get down to indirect through groundwater recharge and indirect through surface water augmentation, and then finally to direct potable reuse, which is the thrust of what we're going to talk about. And again, I just want to, by way of introducing it. Now, if we look at the increase in reuse, and this is without direct potable reuse, you can see that in various parts of the world, a terrific amount of increase is going to be anticipated by 2016, and it's hard to say even beyond that. But let's start with what we mean by indirect and direct potable reuse. We start with sources of water, whether it's groundwater or surface water. It goes through treatment, a community, conventional treatment, membrane treatment, above and advanced treatment. And then there are two paths. One path, the water goes up and it goes to groundwater augmentation. One path goes to reservoir augmentation. And the other path goes, we'll talk about that in a moment. If we take the water from here, we typically take it either into a water treatment system or blend it directly into the community distribution system, and we complete the cycle. In indirect potable reuse, the key thing is that there is an intervention here, an environmental intervention. If we look at the other alternative, we take the water from advanced treatment and we put it into an engineered storage buffer. And from here, we can either introduce it to the head end of a water treatment system or blend it directly into the community distribution system. So our two types are, one, indirect has an environmental buffer. Direct has an engineered storage buffer. And we'll talk about the differences between those two. So if we look at the types of projects first, to give us some perspective, this is the Orange County Water District, and it's rather well known. And the idea is that there are two treatment plants here. The Orange County Water District processing facility is here. Advanced water is produced here and is transported all the way up to spreading basins. They also use some of that for barrier injection wells, and they're now also talking about mid-basin direct injection. So this is kind of the gold standard right now in California. But there's some things that are strange. Here is the reservoir that they use to infiltrate the water. They also use this one and this one. Now, the thing that's a little bit strange about this is that we produce this water. We've actually done everything to it but beat it with a stick. So we take it up here and we put it in this open reservoir. And we allow geese to defecate in it. I don't know if you've ever seen goose poop.
Yes.
Tremendous. I mean, just one poop will give you more coliform organisms than you could ever imagine. So it is a bit strange, you know, and I've always argued that with them. But anyway, this is a infiltration basin, and it has both fish and, interestingly enough, geese that used to go further south now stop here. Why? I mean, you've got this nice warm water, it's pretty clean, and you have a good time. Now, simultaneously, I want to show you, this is the Santa Ana River. The Santa Ana River is the water that comes down is tertiary effluent, and stormwater runoff and highway runoff, and it's infiltrated in these series of diked off areas. Now, the thing that's interesting about this is with respect to regulations. We can infiltrate this water that contains heavy metals, it contains surface runoff, it contains all these things without any treatment at all. Why? Because it's considered waters of the state of California. On the other hand, if you want to do direct potable reuse, you've got to go to these Herculean efforts. And so we're going to talk about regulations later because all of you are going to be responsible for modifying the regulations that we have. typical injection well, nothing special about that. You're familiar with these. They're very similar to your deep well injection wells here in Florida. Here is a typical infiltration basin here in Florida. And it's really interesting because of the soil condition. They've never been able to fill these up with water. They spread the water and never been able to fill it. And if you Google Earth Florida in the center part of it, you see all these things that look like hot dogs. They're all spreading basins. And so there's a huge amount of indirect potable reuse that's going on here. Now, in San Diego, the thought is that we will take effluent from a treatment plant and we will pipe it directly to San Vicente Reservoir. We'll introduce it there, and from there it'll come down to the Alvarado Water Treatment Facility and then be distributed. Now, I'll talk about all of this spaghetti in just a moment, but the concept there is we're going to take wastewater, we're going to treat it, and we're going to inject it into the surface water reservoir. Here's the surface water reservoir. This is San Vicente. Rather a lovely place. Now, let's take a look at this. So if we pictorially look at this, if we talk about Orange County Water District, which is shown up above here, we take the water from a wastewater treatment plant, we treat it in a reclamation plant, and we inject it, whether it's surface or by wells. In San Diego, Singapore, and Australia, they take the water and they're going to introduce it into a storage reservoir. In Windhoek, Namibia, what they do is they have the wastewater treatment plant, water treatment plant, and 30% is injected directly in front of their water treatment plant. Now there's something really interesting that happened in Namibia. They told the public that this thing is going to turn on Monday. They get phone calls you cannot imagine. Everyone calls up, I drank the water and my eye turned purple. Or I drank the water and my pants fell off. I'm just incredible things. And in point of fact, they had never turned the water on. They didn't turn it on until 3 months later. So it's been very, very successful. But it's just an interesting story in why we have to do a lot more with public perception. Why that becomes so important in what we're thinking about doing here. Now, the driving forces, there are any number of them, but I would just like to comment on 3 of them with you. I'd like to talk about population growth, especially along coasts, infrastructure requirements, and de facto unregulated indirect potable reuse. To me, this is the most significant factor. It is projected that maybe up to, I have 70, but some people project 80% of the world's population is going to live within, let's say, 120 kilometers of a coastal region. Now, think about it. You're now going to take water from the interior of the country, bring it to the coast, use it once, and dump it. It is unsustainable. And I'm not going to go through all of the rationale, but if you sit down with pencil and paper, you'll find that it's unsustainable. And as you move more of the population down, and you take more water from the upland, you change the upland hydrology, and then it becomes very significant. And we want to avoid, if we can, unintended consequences. So, anyway, first of all, it's going to be unsustainable. Let's look at Sacramento. When I was first started at UC Davis, the Sacramento wastewater treatment plant is circled here, and there wasn't a single house here, not a single house. And what's happened is that urbanization now has complicated our lives with respect to reuse. People would say, well, why don't you reuse this water for agriculture? Well, now you've got to pump it somewhere. And I'll talk about pumping costs in a moment. But urbanization all over the world has affected us dramatically. And you'll recall, the way we located treatment plants historically, we found locations that would drain by gravity, and the reason was that we used steam pumps in the early 1900s that were not reliable. And so gravity was thought as the solution to get this water out from the city. But what happened now is all through the country, treatment plants are now surrounded by urbanization. The next example is the Hyperion wastewater treatment plant in Los Angeles. Here's Hyperion. The airport here, Los Angeles Airport, is here. So you look at this treatment plant. A study was done, and if you were to pump the water from Hyperion to North Hollywood, which is an elevation difference of 38 feet and about 38 miles, it would take more energy than it does to treat it at Hyperion. And so all of a sudden you can see that these coastal treatment plants were all planned well, but they really didn't envision the urbanization that would take place. Now, another thing that we talked in the past, what we've done is we've put in a lot of purple pipe. And the interesting thing is, this is San Diego, there's an enormous amount of purple pipe, but at the end of the day, you say, how much water has actually been recycled? A very small amount, 2 mgd or something like that. Golf courses take some of the water, and then what they say is, oh, by the way, store it for us over the winter. Really a non-starter. Going forward, it's my belief that purple pipe is a terrible investment. It's a terrible investment for the following reason. What it tells the public is that we don't believe the water that we put in the purple pipe is as good as the drinking water. And we're to the point now where our wastewater treatment facilities essentially produce drinking water with very little additional infrastructure. So I think that when we start thinking about putting in additional purple pipe where we are today, that it's not a good investment. So if we look at agricultural irrigation, we have long distances, energy and pumping, storage. Landscape irrigation, dispersed nature, cost of parallel distribution. Indirect potable reuse, most communities lack suitable hydrology for either groundwater or surface water storage. Now, unregulated de facto indirect potable reuse. What do we mean by this? Let's take the Colorado River. There are 456 discharge permits on the Colorado River. 256 are active. And so what's important here is you go skiing in Utah, and 2 weeks later you go down to San Diego to go boating with your friend. You drink the water, and you've bonded with yourself. It's like going to New Orleans. You know, you drink the water there, and you always get a warm feeling. You've made 5 other friends. Some in St. Louis and, you know, other locations. Incidentally, the other thing that's really curious here in San Diego is whenever they take this canal down, they always find 5 or 6 car bodies. And all these things are leaking everything into the water. And so when you're in San Diego, you're not drinking pure mountain water. You're drinking really terrible stuff. This indirect potable reuse, for example, another case is Dallas and Houston. During certain times of the year, 75% of the river water between Dallas and near Houston is 75% wastewater. It's pumped out, treated marginally, and that's the water supply for the city of Houston. So this is going on all the time. So the indirect potable reuse generally is uncontrolled, and that's the key that we want to stress. Now, what I'd like to do is talk a little about technologies, because I'd like to start the discussion of technologies in the following way. What would make any of you believe that conventional treatment plants, as we've designed them today, are suitable for direct potable reuse? Why would you believe that? I mean, what would cause you to believe that you've produced an optimal plant for direct potable reuse? We're going to come back to that because it's very important, because you folks are going to have an opportunity to change that. If we look at the Orange County treatment system, we have microfiltration, cartridge filters, reverse osmosis, advanced oxidation, carbon stripping, lime saturation, so forth. So this is the flow diagram. Now, one might question, why do you have cartridge filters here? Well, the reason is that the chemicals that are used for scale control and reverse osmosis, the purity is not great enough, and so you use cartridge filters to remove the residual impurities that are present in those chemicals. Here's what it looks like physically. Here are submerged filters, cartridge filters, reverse osmosis. This one bank is 5 million gallons per day, and here's the advanced oxidation. Each of these reactors is in series, and there are 72 UV lamps in each of them. Now, what's interesting, and as we move ahead, one of the things that we're going to continue to do at treatment plants is we're going to run pilot plants simultaneously. And in this case, what we have is a module up here, and every manufacturer of membranes can put one of their modules in here, and we can compare the performance of that module versus the online modules. And this is an ongoing process at Orange County Water District, and it really gives you an opportunity to test full scale. And I think that as we move ahead, we're going to be doing more of that kind of thing. Here is the carbon CO2 stripper and the lime saturator. Now, people that are inland say, well, wait a minute, if you have reverse osmosis, it's okay if you're near the coast because you can dispose of the brine in the ocean. And there are a variety of other technologies that are being put forth. Microfiltration, ozone with an ozone contactor, biologically activated carbon, and electrodialysis as one option. And it's for sure, in your career, you'll come up with other options for doing this. And this one has proven to be very effective. And again, because it hasn't been tested, the state of California is somewhat reluctant. But that's going to change in time. Now, what's important about these two systems? If we look at the energy use, what we find is that if we look at the MF ozone VAC, it's 0.03 to 1 kilowatt hour per meter cubed. If you look at the MF RO UV peroxide, 8 to 10. So there is a significant energy difference in these two processes. Now, whenever you think everything is new, we need to look at this diagram. This is from 1972 in Colorado, and this was a drawing taken from the patent application. I'll show you the line drawing. Essentially, it was to produce drinking water from wastewater. Now, this is 1972. Here's what the diagram looked like. Way back when, they had biodisc treatment, cloth media filters, way before they'd become even common. We went through microfiltration, ion exchange, UV disinfection, and these systems were used in households throughout Colorado. So the technology is not new. It's just interesting that it's been around for that long. If we look at Namibia, what we have here is the original flow diagram. And then it's become more sophisticated, and now this is the flow diagram that's currently in operation. And again, you can see that they do not do it with reverse osmosis. I put up this diagram not because I want to highlight any specific area, but I want to point out to you that all the dashed areas are up for grabs. They're up for you to propose alternative kinds of treatment technologies. And we'll get to why that becomes important as we move along. Now, let's take a look at system management. Again, this is our system. And we want to, let's say we want to do direct potable reuse. So what do we have to do? What we have to do is, let me back up just one second, and I do want to introduce this stored engineered buffer. Why do we have it there? And the idea is that the buffer can be used in place of an environmental buffer for greater control of water quality. So what kinds of things can happen? Well, here's the typical actual flow diagram of a low molecular weight organic compound. And you can see, typically it goes in at about 8. It's the effluent from the RO is about 0.35 on a consistent basis. And then we got this bleep. And so the idea is that if we get some of these bleeps, we're able to trap them. And the question then becomes, how long does it take to analyze for a specific compound? And we have to determine what are the specific compounds that we need to analyze for. And that's an ongoing question and research topic. And with respect to engineered buffers, they can be anything, above ground storage, subsurface, aquifers. There's no limit to the configuration that they can take. But when we start thinking about overall management, we have to think about wastewater from the very beginning. We have to think about the source. We have to have source control programs. You know, we have obviously conventional treatment, and we have all of the rest of it. But you can see that when you start to think about direct potable reuse, it's a process. It's not just treatment technology. It's the entire process of how we handle wastewater from the very beginning, what we do. And if you think about source control programs, 2 of the most sophisticated are in Orange County and San Diego. With GPS, they can actually tell you where every industrial discharge is. And so they've worked with them with that kind of scheme. And so what I'm saying is that it's this overall system that makes direct potable reuse a viable alternative. Now, let's talk a little about the impact of direct potable reuse on the future of wastewater treatment plant designs. I've talked a little about source control. I'd like to just highlight these ideas with you because I think they're so important. Now, the first one is, why do we accept wastewater the way it comes down the sewer? What do? Well, we remove solids, we remove grit, and we'll settle it, and then we'll say, you know, no matter what it is, we'll treat it biologically. Now, why should we do that? Why shouldn't we alternatively say, how can we modify the characteristics of this wastewater to optimize biological treatment or subsequent treatment? And I'd like to give you 3 examples that we're looking at, and there are many more out there, but let me give you 3. The first one is the so-called cloth filter. And this is a replacement for a 1 MGD clarifier. And you screen out all the bits of plastic, and these things work well. This next one is an interesting process. It's called charged bubble flotation. It's not dissolved air flotation with which you're familiar. That is where you pressurize and dissolve air in the column. You produce a froth. And you then coat the froth particles with a polymer. And to the polymer, you attach nanoparticles for the removal of specific compounds. So all of a sudden now, you can tailor the characteristics of wastewater before it ever gets to biological treatment. Now, the last one is filtration. So we can take primary effluent and we can filter it. And we filter it with what's known as the fuzzy filter. This is just one example. Fuzzy filter are round plastic balls like this. They're porous and they're compressible. And so all of a sudden now, we can filter it, and we produce a very high quality effluent at this point. Now you look at these things, and they do one additional thing that is really dramatic. If you filter primary effluent, what you do is you alter the particle size distribution. And when you alter the particle size distribution, you change treatment kinetics. Now, for example, If you had a large particle coming over a primary clarifier, it might be the size of this table, and this is the size of the bacteria. So the bacteria has to excrete extracellular polymers to cellularize this for metabolism. On the other hand, if the particle is twice the size of my fist, it's just going to take less time. And in a study, plastic study done in 1957 by Baumann at Rutgers, he found that there is the increase in the kinetic rate is up to a factor of 4. So by altering the characteristics, we can change that. Now, we can also do other things. For example, we can take this effluent and we can run it directly through a microfilter. There are no end here to the possibilities. But here's the thing that's important. What are we saying? Instead of incrementalism, that is where we change something on the primary clarifier, or we change the arm, what we can actually do is leap over that. We can leap over that with new technology. And that's where the future lies. Not incrementalism. Because if you think about the way we've done wastewater treatment, we said, let's remove floatables and incinerables. Okay. And then we said, let's remove biological organic matter. So we added another process. Then we said, well, we ought to remove nitrogen and phosphorus. We added 2 more reactors. And then there were still some residual solids, and we added filtration. And that's what I call incrementalism. And that's not going to bring about change in the future. What's going to bring about change in the future is when you leap over those. For example, the cloth filter is a leap over that. It's not a sedimentation tank. It doesn't look like a sedimentation. It performs differently. Charged bubble flotation is 1/5 the size of a sedimentation tank. And these are just but a few examples of what's going on out there in the field in terms of people thinking about how do we make the big jump. Now, for sure, flow equalization, either inline or offline, is a major factor. And I can just tell you that Orange County Water District operated with effluent from the sanitary district, and it had a diurnal variation like this where you were sitting. And as a result, they ended up developing stress cracks in their membrane system who are connected to the wall, and so they're going to flow equalization. And not only that, when the treatment plant started nitrifying, performance improved by 30%. And so the idea is we need to think about how we're going to deal with this. On return flows, typically we return thickener overflow supernatant concentrate back to the head end of the headworks or sometimes in front of the aeration tank. Now the problem with that is that we tend to return these flows during the daytime hours when operators are present. And what that does is it complicates the treatment because instead of introducing it, let's say, in the off hours when you have excess treatment capacity, you're now introducing it when your system is stressed. And then you bring in things like organic carbon that's non-biodegradable, and then you're saying, well, why can't we meet our nitrogen limits? And so on this, I'd like to stress why this is so important. In San Diego, the city of San Diego said, we're going to pilot the treatment system that Orange County Water District has used. And, we asked them, why don't you pilot other things? And they said, that's really not our interest. Our interest is in getting this approved. So they piloted the same thing. And they started monitoring everything, and they thought they would find exactly the same stuff. Works out they found nothing. And the reason was that it's a scalping plant. It operates at constant flow, and all the return flows are directed to Point Loma. They never enter the treatment plant. You cannot imagine the improvement in performance when you do that. For example, Tillman, which is the treatment plant in Los Angeles, operates at constant flow, their turbidity coming off the clarifiers is less than 2 without any intervention. And so what I'm saying to you is that if we start thinking about direct potable reuse, we're going to have to think a little bit differently about how we design our systems. Now, suppose I asked you, you're all students on an exam question, what's the end point of activated sludge? What would you say? Okay.
18%.
How many would say discharge to the environment? Well, wait a minute, if it's not discharge to the environment, where the hell is it going? Okay, the point I'm making here is this. If your endpoint is discharge to the environment, what are you concerned about? You're concerned about nitrogen, you're concerned about phosphorus, you're concerned about all these elements. But what if I told you the endpoint of activated sludge treatment should not be discharge to the environment, but it should be as influent feed to a membrane system? It works out, you would design your process differently. You would not design it the same way. And we know how to do that. You would design it, for example, perhaps to remove trace organics or other kinds of compounds. But the thing that you really would ask for is you would ask the membrane people to tell you, what kind of quality do I need to optimize the performance of my membranes? And then you would work backwards and say, all right, how do I design the activated sludge process to give me that kind of quality? And so the key point here is, in the future, think about different endpoints. You don't have to always think about discharge to the environment. It could be discharge to a membrane, it could be discharge to reverse osmosis, and who knows what other processes will come along. And so the key point is that we need to now start thinking differently about the processes. In other words, we tend to teach activated sludge as an end-all. It's the end of the world. It's only the beginning as we move ahead. Now, I hesitate to put this up, but here is a complete treatment process without activated sludge. So we're going to adsorption, zeolite ion exchange, ultrafiltration, reverse osmosis, gas oxidation, purified water. And then we process the solids here with a pyrolyzer. And I was talking, it was really fun being here. I was talking to Dr. Cooper, and this matched up with some work that he's doing directly. We go over here, we produce power, but we also produce biochar, and we bring back that biochar, and that becomes our adsorptive medium here. Again, what's the purpose of this diagram? The purpose of this diagram is to let you know that you're not locked into activated sludge. Now, you might say, well, I don't think it'll work. That's okay. I don't mind that. But it's certainly a concept that we ought to test. It's a testable concept. And the pieces work. So it's a question of how we want to think about it. See, look what we've done with activated sludge. We've tinkered with it. We started, and then we had filamentous, and we figured out how to do surface skimming, and we did all these things. But incrementalism. So how do we leap over activated sludge? I'm not suggesting that we should, but if you think about it, how should we leap over activated sludge? Again, this is just a thought piece. I wanted to talk, before I do this case study, I wanted to talk a little about the effluent here. What's interesting is that people are concerned about endocrine disruptors. And typically, you might have 20 parts per trillion of an endocrine disruptor. The interesting thing is 20 parts per trillion of an endocrine disruptor will cause sex reversal in fish. On the other hand, and you folks can do this computation, you would have to drink 496,000 8-ounce glasses of water to get what a woman gets in a single birth control pill. So, if you're really interested in saving the environment, what's the answer? You should drink it. I don't see much enthusiasm for these ideas. All right, so let me give you a DPR case example, Southern California. Here's a picture of Southern California, and on the left-hand side, we have the pumping. Here's the elevation difference that we have to go over. There is energy recovery, but we have to pump this water over the Tehachapi. If you're going to, let's say, reuse it, you can't imagine pumping it back, because this already takes 20% of all the energy in California. So let's take a look at supply and conveyance. In Northern California, it's about 150 kilowatt hours per million gallons. Southern California, it's 8,900. 8,900. And that's why, really, this becomes, as you think about it over the long haul. Now, look what happened. Look what's happening in California. Our governor wants a monument. Your governor wants to tinker with education, but ours wants a monument. What does he want? He wants to build 2 twin tunnels around the periphery of the delta here. And these tunnels are projected to cost $30 billion. Now, if this is like the Boston dig, if you recall, the Boston dig was going to be $3 billion. It's now $16 billion and counting. All right, so keep that in mind. So what's the proposal here? Well, the proposal is as follows. That what we'll do, instead of discharging here, we'll treat all this water locally and we'll provide purified water. Now, how many of you drink bottled water? Come on, fess up. Okay. Now, here's the interesting thing. You pick up this bottle and it says, purified water. Did you ask if it was wastewater yesterday?
It probably was.
Could be. But you're good to go, right? It says purified. So, public perception is an issue. And while we're talking about public perception, before I get to the answer, public perception about water reuse depends on how you ask the question. So, if I came up to you and I said, are you willing to drink wastewater? And you'd say, oh, I might have to think about that. Oh, God, I don't know. I mean, what the... On the other hand, if I show you the picture of the Colorado River and the fact that you're drinking really terrible stuff, it works out that attitudes change. And in San Diego, right now, 67 to 73% they favor direct, indirect, and direct potable reuse. City of Los Angeles has an enormous groundwater basin, and they're talking about it's contaminated with TCE, PCE, Chrome 6, Chrome 3, and other things. So they did a survey of the public. They said, which would you favor? Treating the groundwater and drinking it, or treating wastewater and drinking it? 8-to-1 treating wastewater. Why? Because they don't trust the city to treat that water. And yet they've seen the Orange County Water District system, and perfectly comfortable. All right, so now, if we do this, how can we do this? Well, it works out that Los Angeles is decentralized. And that's a really interesting phenomenon, because there's a lot of talk of decentralization in small systems. But here we have a very large system. And this is the Tillman plant, Glendale, and this is the Hyperion, the plant that we looked at, discharges to the ocean. This is Los Angeles County Sanitation District. These are the upstream plants, and this is the joint plant, discharges to the ocean. We could locate a water treatment facility at each of these locations. I just put it there for purposes of comparison. And it works out that I can treat 1 billion gallons of water a day, the same amount that would be transported with the system before treatment, for $5 billion. And so my point here is that at least we need to think about these alternatives. There's a huge difference. And I can give you 2 stages of reverse osmosis if you're not comfortable with one. And so, you know, we now have to start thinking differently about the way we do things. The benefits, you know, you got a reliable source, low cost. Let me give you an example. Orange County Water District now treats their water, and the cost is $785 an acre foot. And an acre foot is about 323,000 gallons roughly. Raw water now is selling in Los Angeles for $1,000 an acre foot. And in your lifetime, water's going to go up by a factor of 10. Absolutely. It's highly subsidized now, but we're moving into an era where it's really going to go up. So, I'd like to say something about regulatory requirements. You know, pre-1880s, we had physical observations. You know what they did? They took a sample of water, and they put it on a windowsill. And if it developed growths, it was probably not safe. But they were already dead, so it didn't matter much. So we had to have some better methods, so we developed some empirical methods. So the period of enlightenment, 1880 to 1980s, science develops, and observational and semi-empirical regulations evolve. You know, for example, in California, for reuse, we have an effluent turbidity of 2. And you say, how did that come about? Through science? No. It came about because it was achievable. That standard has no bearing in science, no bearing in anything. It was achievable. All right. The problem that all of you are going to face in your career is that you're going to have to deal with the fact that science has leapt ahead, but we still have semi-empirical and empirical legacy regulations. And as you develop new concepts and ideas, you're going to have to deal with the health department and try to explain to them why, we ought to move ahead. And it's a real challenge. The next thing is the need for a uniform vocabulary. And here, what's the issue? The issue is not everyone agrees that indirect potable reuse is acceptable, but there are little standardization of terms. So as a consequence, everyone says whatever suits their particular interest. And so if we're going to have a meaningful dialogue about direct potable reuse, we need a set of definitions so that when I speak to you, it doesn't go off into space, and when you speak to me, it doesn't go off into space. Because unless we do that, we're all talking around the subject. We never really understand each other. Closing thoughts. I'm convinced personally that direct and indirect potable reuse is inevitable in urban areas, and it's going to be part of the water sustainability future. The key to all this is we have to think differently about water. It is no, wastewater especially, it is not a waste. It is a resource. Technology is not an issue. The public is supportive. And really, we need bold new planning now. One of the things that we should do immediately is municipalities have silos. Here's a water treatment, here's wastewater treatment. Those should be brought together almost immediately. And finally, what I'd like to leave you with is that we've talked about regulations, but in the 20th century, regulations were what drove innovation, or drove treatment. In other words, as we got more rigid standards, we had to add one more process. We did one more thing, incrementalism. In the 21st century, I am convinced, not only here in the United States, but worldwide, the value of water will drive development. It will drive development because it's a truly valuable resource. And because it drives development, we will lead the health departments, not be subject to it. I'm absolutely convinced. And that means that we really need to accept the value of water, but that the water is so valuable that treating it to, let's say, with double reverse osmosis is inexpensive compared to the value. Now, Tom Friedman wrote an article in the New York Times a couple Sundays ago. There are potentially 42 million people in Iran that might have to be moved because of the lack of water. Can you imagine what a migration like that will do to the Middle East? It's just amazing to contemplate. And there, the value of water will drive what happens in most of the world. And certainly in our drier southwest regions and elsewhere, that will be a major focus. And with that, I'd like to thank you for listening.
Don't you guys have any questions?
You know, the interesting thing, Doctor, is that at RecTech this year, I saw two companies promoting technologies. One was an MBR company that had that high-rate primary clarifier ahead of it. And another one was a company that had a high-rate dissolved air flotation separator in front of activated sludge.
Right.
And so I think the market is starting to see, and what you're talking about, and they're looking at those solids that they're taking out using the dissolved air flotation and the high rate primary as an energy source, potential energy source.
Well, it's really interesting because not only do you recover the energy, but let's take the following example. Suppose you filter primary wastewater, and the soluble BOD is about 60 or 70. So instead of going into a carbonaceous reactor, you now go directly into a nitrification reactor. You bring the effluent back to denitrify, and there's barely enough carbon to denitrify. So you never have to treat the carbonaceous part of it. Think about that. So, you know, and then there's the Atomox process and a variety of other technologies that are out there. And again, the key thing to all of this is there's no limit to what you can think about. You know, and you're not bound by the fact that we've done it. Think about it this way. Many of you are civil engineers. We haven't changed civil engineering education in 100 years. The only thing we did is we dropped railroad engineering. Railroads, what other field has not changed? And so all I'm suggesting, and you're right, I mean, those two examples are two parallel, and people are now starting to see that you can recover additional energy, and you can spend less energy on treatment. Other questions? Yes?
How does politics trying to transition from, traditional water treatment to what you...
Okay, the question is, how do politics play into transitioning? Probably the best example I can give you is San Diego. And what San Diego has done is they have developed an outreach program where they go out and talk to small groups, and then they bring any number of groups to the treatment process. At the end of the process, everyone drinks the water. Now, what's interesting, the city council voted 8-0 to go directly to indirect potable reuse by augmenting the reservoir, but they instructed the staff to route the pipeline right by the water treatment plant and not bother going all the way. So the populace is really driving it, because when you explain all this and you look at the water, everyone says, why do you take that pure water and degrade it in a reservoir and then treat it again? So it's a, it's an interesting debate.
And I was also wondering about the regulatory environment, because I know that we have all these restrictions in the state of Florida that you aren't allowed to put it, you're not allowed to put it in the ground, you're not allowed to reuse it directly. What does one do about that?
You're going to work hard. All of us have, have to keep talking about it, because these regulations do have to keep up. State of Texas now has a large study on developing guidelines for direct potable reuse. And NWRI is talking about it. And I think that these agencies will inform and actually lead the states. In California, what happened was that the health department is going to be moved from the Department of Health to the Department of Water Resources, the Resources Control Board. Although it's not firm, but that's generally the plan. And part of it is because they were so recalcitrant in making any decisions about anything. Now, it's different if you have, let's say, my own community of 65,000, let's say we were interested in direct potable reuse, that's fine, but no clout. But now we have the city of San Francisco, San Jose, Los Angeles, San Diego, and together they have huge clout in terms of getting people to think about these things. So I think that, yeah.
Yeah, I think we took a aerial shot at the Hyperion wastewater plant and talked about the energy it would take to pump that back up to Hollywood. It just makes the argument for decentralization. So it's understandably these facilities have to go because gravity takes all the wastewater there in the central location. But if you want to reuse, then that really I think makes the argument for decentralization.
Absolutely.
Of your facilities. Now you made that point with LA and you showed where that could work. So it's really kind of a comment about the decentralization and building off of her comment. So the LA Basin is managed by LA City and LA County, and to what degree would that potentially get in the way of something like this happening, where you've got two government structures over the same watershed?
Believe it or not, they're talking to each other, and it's really interesting. You know, 2 years ago, I shared a panel from the city of Los Angeles, and we suggested this. And it was like a dull thud in the room, you know, who invited this person? 2 years later, believe it or not, they're talking about it, and they're talking about taking water from the Tillman plant, pumping it up to a spreading basin, and then they'll tell you, well, you know, it's only a few more miles to the head end of a 600 MGD water treatment. So I think things are going to happen. You know, the technology is really not the issue, you know, I mean, and it's getting better all the time. And so I think that more people have to be exposed to the idea. How many had heard of direct potable reuse before? Okay. This is an educated group. That's great.
I was just wondering about your thoughts on how context and with not the same scale impact the decision to, treat the effluent to higher levels for direct potable reuse versus this idea of, matching treatment level to the end use application.
The latter, the matching the end use to the treatment objective is not really well appreciated, because if you look at the literature, the amount of work, for example, phosphorus removal, there is so much work now on reducing the variability, the natural process variability to get phosphorus levels down. Well, if membrane systems were your endpoint, you really don't have to do that. But, and so, again, it's a difference in the way we think about these things. Now, you could argue, why shouldn't reverse osmosis be part of the treatment process? Interesting bit of information. The Department of Water Resources did a study, and they said, okay, what would the next gallon of water cost in Southern California, regardless of where you got it? Let's not worry about that. And they estimate $1,000 to $10,000 for the next gallon. Because there's been an adjudication, less water is coming down the Sacramento, and Colorado is utilizing more water, and it's getting drier. And so, when you think about this, these costs are going to creep up. In my mind, they're going to creep up to where new water will cost you a couple $1,000 an acre foot. You can treat this water for $750 or $780 an acre foot. So part of it is that we've not thought about this much, and we've not taught this very much in graduate schools or undergraduate schools. You know, I mean, we teach, I understand that, you know, we all need theory, and you all need theory, but you also need to put that theory in the context of a larger picture of what might be possible. There's another, yeah.
From an economic standpoint, what is the recovery period for the improvements made to the water treatment plant to convert to this process?
Well, Orange County would have to buy water at $1,000 an acre for it, and then still treat it. And so for them, the payback period is about, well, they're expanding their plant now to 125 MGD. So their payback period is about 7 years. Don't quote me on that number, but that's kind of the range that it's in. And what that means is that that number is going to get better. You know, we're going to get smarter with the technology. You know, I've been around now to 5 different schools, and I look at the technology and I marvel. You're going to marvel. The things that you're going to see in your lifetime will be astonishing. And you've got to be prepared not to say, well, you know, we ought to put in a SED tank. You've got to put in whatever's out there that makes sense. Question? Was it? Yeah.
So you mentioned technology is not an issue and how it's supportive. I'm just wondering from your perspective, what are the knowledge gaps in the area of direct potable reuse?
I think part of the knowledge gaps are how to develop effective source control programs, you know, in a broad sense, how to design the engineered storage buffer. And water reuse has a large study on that right now, and the idea is you would like that storage buffer to at least store enough water consistent with the rapidity with which you can make critical test measurements. But the other thing that's happening that's so dramatic is the development of sensors, and that field has just mushroomed. You know, and before, you know, we didn't have sensors for this, that, or the other thing. Now we have them for everything. How to use them effectively is another matter. I mean, that's open to debate. But, I mean, really exciting ideas on the sensors. Yeah.
Source reduction. So I think if I was a community member, I would be more acceptable of that vision if people were doing something to implement source reduction. So we're going to be really strict in enforcing pre-treatment standards. And in terms of like our wellness, our health system is based on meeting a doctor for 10 minutes and they prescribe pharmaceuticals versus spending more time to figure out how to make you well without taking pills. And so I'm just kind of curious, when we were talking about the dialogue between different units of government, it seems like our profession has to go back to having dialogue with public health people, you know, consumers. Why do some of us use fragrances in our soaps and other people don't? So could you kind of talk about that?
Well, let me talk first of all about the physical aspect. So, how many have low flush toilets? You know, when low flush toilets were proposed, every city adopted them because it was such an easy way to save mankind. Such an easy way to save mankind. But look what's happened with low flush toilets. You flush, and the solids remain in the collection system because there's not enough water to transport them. Hydrogen sulfide is produced. It's okay locally, but it's transferred with the water that we supply, and it's going down and it's corroding all the concrete pipes that we have further into the system, the larger pipes. That's going to be astonishing. The cost to replace that infrastructure is going to dwarf everything else, dwarf what we're doing here. And the other very interesting thing along that line is water use per capita is going down. Now here's the interesting thing. From where you're standing, let's say up until about 1992 there was a line like this. Now, it could be higher or lower depending on the city. But since that time, that line now has started to come down. But the interesting point is, we know that at some point it'll flatten out. It'll flatten out at around 40 gallons per capita per day. But we don't know where this line is. Why? Because if you take any of the cities here in Florida, you don't know how many washing machines with 40-gallon tubs are still out there. 5 years from now, you'll only be able to buy a washing machine with 10 gallons per tub. So we're coming down. And so here's another question I pose to you, and then I'll get to the one that Jim is, what would make us believe that we could reduce the water by 50% or 100% and still have our collection systems work right? And why would you believe that? I mean, what evidence is there, that you could do that? In fact, there is none. And it's one of the things that we're going to have to consider. And that is that it was a wonderful idea. Low-flush toilets, saving mankind. And yet, you look at the cost of the infrastructure and what's going to happen, it's going to be amazing. Now, on the products that Jim was talking about, I think that I guess I am not as optimistic on how we're going to my mind, those should be regulated so that, and the thing that may happen is that as water becomes scarcer and municipalities have to think about blending, reuse and blending, I think you may well see ordinances banning certain kinds of compounds because of the problem, in terms of treatment. But, with the endocrine disruptors, it's really interesting that this 20 parts per trillion causes sex reversal in fish. My chair is a woman, and she says, you know what? A little less masculinization is okay. But it's a bit of an issue, and I think that it's going to happen out of necessity. I think that's really what's going to happen. And some municipalities have dealt with it in terms of outlawing certain things, but it's a very difficult, because it smacks of control and all the rest. But if you're in a water-short area, for example, there are communities in Texas where the brine from reverse osmosis dilutes their drinking water. Big Spring, Texas is one. The water, the TDS is 3,000. If you're not used to it, you take a drink of 3,000 TDS water, and you better be near a restroom. I mean, there is no way out. I always laugh, if you have metal fillings, you can tune in Wichita and your mouth through this water. Any other questions? Yes?
What do you think about natural methods of wastewater treatment, like vegetative ponds or wetlands, because it could be like a good link, like good connection between wastewater treatment and
I think they're quite grand, but the limitation is the land required to make them work. Now, for example, here in Florida, I'm trying to think which university did a lot of work on radiation of sludge. And so I was at this conference, and I said, well, okay, you're going to radiate this sludge, and you have a slot. How wide is this slot? Like 1/4 of an inch. Well, it's great. It works great. But think about the city of Chicago. You're filling this room every 10 minutes with sludge. How are you going to get it through some small slot? And so there are really a lot of wonderful ideas that just aren't going to go. The other idea that everyone has is that, gosh, we can recover all this value. But if you look at the methane from small treatment plants, and you put in digestion facilities and recovery, you just simply cannot make a case for it economically. Now, talk about, again, other unintended consequences that you never think about. Think about anaerobic treatment of the complete waste stream. So people are talking about, let's do that. Now what happens when you've contained it so you can recover the methane, but in the headspace now you have methane at more than 1 atmosphere, and so now you're increasing the concentration of methane in the liquid. So when the liquid flows out of your reactor, you're discharging an enormous amount of methane to the environment. So if you're concerned about carbon footprint, that's a bit of a problem.
I had actually one question.
Yes.
It's more than 40 years since the Clean Water Act, and that period we had a major federal investment in municipal wastewater treatment plants, and I'm thinking that a lot of them are reaching their end life. Is there any chance of a federal program to try to institutionalize the use of wastewater and not treating it as a waste but rather as a resource?
I wish I could say our government was functional. I think it's going to be very difficult. What I've observed across the country